ourselves going. So we've got a horizontal wall, we've got a frictionless surface, we've got a spring, and we've got a mass. Now this mass is given as being 3 kilograms. Over here it is at position x equals 0, and the force from the spring on the mass is also equals to 0. We consider our system to be just the mass and the spring. Now we're going to approximate this spring to have a negligible mass. Negligible mass. Pardon my spelling. So we essentially just assume that the spring has got no mass. So if it doesn't have any mass, it cannot have any kinetic energy. Now, if you look at this, immediately you see, well, if I just consider the mass and the spring to be my system, there's got to be a normal force from the surface, there's a weight downwards, but none of those two forces can ever do any work on this mass if the displacement remains on the horizontal, because the normal force and the weight are perpendicular to the horizontal. Since work done is the dot product of the force with the displacement, two vectors are at 90 degrees, the dot product is 0. So a force that's 90 degrees to the displacement cannot do any work. So neither the normal force nor the weight in this case can do any work. The only force that can do work is the external force that we are now applying to this mass. And we get that because of this external force, at some later time, the mass is over here, and that is equals to 1 centimeter. We still have our external force, but we now also have a non-zero spring force trying to pull the mass back. Here we say just the instant after the external force was applied to this mass, it had a constant velocity. So if this force is just being applied and this mass has just started moving, there has to be a spring force just the instant after that starts to counteract the external force. Otherwise, this mass would accelerate, and that we're given that this external force is just applied so that the mass moves at a constant speed. And at some later time, the mass is farther still. So now it's 2 centimeters away from its equilibrium position. Still we've got an external force applied. Still we've got a spring force opposing. So these 3 instants, and we now need to calculate first of all the potential energy of the system at all 3 of these instants, the kinetic energy of the system, and then figure out if there's some link between the potential energy and the work done by the external force. So let's figure out the potential energies first. Just want to get to my, there we go. So let's look at this case first. So the only potential energy the system can have is the elastic potential energy stored in the string. Right? If the spring wasn't there, and we remove the external force, this mass would go nowhere. But because the spring is there, if we stretch it out a little and let go, the mass can move back to its equilibrium position. So there's some amount of energy that's stored in the spring, and we call that just the elastic potential energy of the spring. Right at this instant, the elastic potential energy of the spring is 0, because the mass, it's just started moving, but it really hasn't been displaced. It's been displaced by an infinitesimally small amount away from x equals 0. An amount so small that it's as small as it can be without being 0. So to a very, very good approximation, here our potential energy is equal to 0. Over here, our potential energy has increased because now the spring is being stretched out. So if I were to remove the external force, this mass can start to accelerate in that direction. So it can gain kinetic energy. So at this position, it's got the potential to gain energy because of how far away it is from equilibrium. So there must be a certain potential energy associated with the system. We know what this is. For a spring like this, we know that the potential energy at any time is equals to a half times kx final minus a half times kx initial. Right? Remember, we're not interested in the work done by the spring force. That would have been x initial minus kx final squared. Sorry, got the squares. So we're interested not in the amount of work that the spring force will do eventually in putting this mass back. We're interested in how much energy can it gain, possibly, because of its position at this point. And that's given by that expression. We know this is equals to 0 because x initial is equals to 0. So our potential energy in this case, just draw a line here, is equals to a half times the spring constant is given as 5 newtons per meter, and the final position is 0.01 meters squared. And if we calculate this number, we get 0.025 joules. So make sure 0.02025 joules. Just move it over. There we go. And the same thing goes over here. Here we've got that the potential energy of the system is again a half kx final squared minus a half kx initial squared. This thing started out at x equals 0, so this term is equals to 0. What's left is a half times 5 newtons per meter times 2 centimeters squared. And if you calculate that, what you get is this is equals to 0.001 joules. Question? Yes? That's the thing. We're moving away from that now. It is generally true that if there's an amount of work done on an object by a resultant force, that that amount of work is equal to change in kinetic energy. Here the resultant force on the 3 kilogram mass is 0 the whole time. So the applied force is just enough to counter the spring force at every point. We know that means it cannot accelerate, which means if it had an instantaneous velocity, it will be constant. So we've got 0 work done by the resultant force, so no change in kinetic energy. And that's basically the next thing we need to do. We need to figure out what is the kinetic energy here. Well, it will be equals to a half times m times whatever the speed is squared. Same thing over here. When the mass is a centimeter away from its equilibrium position, if it has been moved with a constant speed, we get the same kinetic energy there and the same kinetic energy over here. So the kinetic energy doesn't change, but the potential energy, again, we see increases from being 0 to being 0.0025 joules to being 0.01 joules. So again, we find that somehow energy is transferred to the system, and that increase in energy, it's stored as elastic potential energy in the spring. We can calculate how much work is done by this external force. So the work done by the external force when the position is 0, so we have got no displacement yet. Now, we said that the work done by the spring force in moving this object, say, from here to here, would be equals to a half kx initial squared minus a half kx final squared. And the work done by an external force must be just enough to counter this. So if the spring force were to try to add this amount of energy to the system, the external force just needs to take away so much energy for everything to be balanced. So we know the work done by an external force, in this case, would be equals to a half kx final squared minus a half kx initial squared. We have no displacement yet, so x final is equals to x initial if our displacement is 0. So the work done by the external force would just be 0. So before we've got a displacement, we cannot have work done. Now if we look at the work done by the external force when we have a displacement equals to 0.01 meters. So this mass has now been displaced by 1 centimeter, which means work had to be done. How much work has been done? We've got the external force. The work it does is a half kx final squared minus a half kx initial squared. This is a half times 5 newtons per meter. The final position is 0.01 meters squared, and we started out from position x equals 0, and this is just equals to 0.0025 joules. And you can do the same calculation for the work done by the external force when the displacement is equals to 2 centimeters. Now what you find is the work done is just equals to 0.001 joules. So if you do this calculation again, you find that the amount of work done by the external force in moving this particle object a certain distance is equals to the increase in the potential energy of the system. So again, we've got an external force transferring energy into the system. The system takes that energy and stores it as potential energy. What that means is, if we were to take away the external force all of a sudden, the only thing acting on that block would be the spring force, which would try to pull this block back to equilibrium, so it would gain kinetic energy. So it has the potential to gain kinetic energy at this point. It's 2 centimeters away from equilibrium. So the potential energy of the system has increased.